Welcome back. Today we're learning Gated Recurrent Units, or GRU. This is one of the most elegant ideas in sequence modeling. It solves the same problem as LSTM, but with a leaner design. Let's build it up step by step. So why did GRU come along at all? Plain RNNs forget long-term information. That's the vanishing gradient problem. LSTM solved this beautifully with a separate cell state and 3 gates: forget, input, and output. It works, but it's heavy, with a lot of parameters. GRU asked a simple question: can we get the same memory control with fewer moving parts? And the answer was yes. GRU merges the cell state into the hidden state itself, and it uses only 2 gates instead of 3. Let's look at what goes in and what comes out. The inputs are xt, the current input at this time step, and ht-1, the previous hidden state, which carries memory forward. These two combine and pass through 2 gates and 1 candidate state, to produce ht, the new hidden state. And here's the key difference from LSTM: there is no separate cell state line. GRU keeps everything in a single hidden state stream. That's the whole simplification, in one sentence. We start with 2 inputs, the previous hidden state, ht-1, carrying memory forward, and xt, the current input. Both flow into every gate from here. First, the reset gate, RT. It's a sigmoid over the inputs, giving a value between 0 and 1. It decides how much of the past to forget when we build the new candidate memory. Close to 0 means ignore most of the past here. That reset gate scales down the previous hidden state, which combines with xt and passes through tan. This gives us h-t, the candidate hidden state. Think of it as GRU's draft of what the new memory could be. In parallel, the update gate, zt, also a sigmoid over the same inputs, decides the balance between old memory and this new candidate. One gate here does the job that forget plus input did in LSTM. Finally, everything merges. The new hidden state ht is a blend, 1 minus zt, times the old state, plus zt times the candidate. Zt near 0 keeps old memory, zt near 1 adopts the new candidate. One equation, and the update is complete. Let's now compare all 3 architectures side by side, starting with the simplest, vanilla RNN. At every time step, the previous hidden state and the current input are combined and squashed through a single tan to produce the new hidden state. That's it, one operation, no gates at all. It's simple and fast, but it has no mechanism to protect long-term memory, which is exactly why it suffers from vanishing gradients on long sequences. Next, LSTM notice the extra line running along the top. That's the cell state, CT, which acts as a protected memory highway. 3 sigmoid gates control it. The forget gate decides what to erase from the cell state, the input gate decides what new information to write in, and the output gate decides what part of the cell state becomes the visible hidden state. Powerful and precise, but 3 gates plus a separate cell state means more parameters and slower training. And finally, GRU, the one we just learned in detail. No separate cell state line, everything lives in the hidden state. Only 2 gates, reset and update. The reset gate shapes the candidate memory, and the update gate blends old and new. Fewer parameters, faster to train, and in many tasks it performs just as well as LSTM. Here's the full comparison in one table. Vanilla RNN has no gates and no long-term memory protection, fastest, but weakest. LSTM has 3 gates and a separate cell state, strongest memory control, most parameters, slowest to train. GRU sits in between, 2 gates, no separate cell state, roughly 25 to 30% fewer parameters than LSTM, trains faster, and on many mid-sized datasets performs comparably to LSTM. The rule of thumb: try GRU first when you want LSTM level performance with less compute, especially useful for a clinical time series problem where your dataset isn't huge. Quiz time. Question 1. How many gates does GRU have, and what are they called? Take a moment. The answer: GRU has 2 gates, the reset gate, RT, and the update gate, ZT. Unlike LSTM's 3 gates, forget, input, output, GRU merges the what to forget and what to add logic into a single update gate. Question 2. What replaces LSTM's separate cell state, CT, in GRU? Tap to reveal. The answer, nothing separate. GRU merges the cell state and the hidden state into one single stream, HT. This is the core simplification that removes an entire set of parameters compared to LSTM. Question 3. In the final blending equation, what happens when ZT is close to 0? Tap to reveal. The answer, when ZT is close to 0, 1 minus ZT is close to 1, so HT is approximately equal to HT minus 1. The network keeps almost all of the old memory and barely updates, useful when the current input carries little new information. Last question, why would you choose GRU over LSTM in practice? Tap to reveal. The answer, GRU has roughly 25 to 30% fewer parameters, which means faster training, lower memory use, and less risk of overfitting on smaller datasets, while often matching LSTM's accuracy. LSTM may still edge ahead on very long sequences that need very fine-grained memory control. Let's summarize. Vanilla RNN is 1 tan, no gates, and it forgets fast because of the vanishing gradient problem. LSTM has 3 gates plus a separate cell state, strong long-term memory, but heavier. GRU has 2 gates, reset and update, no separate cell state, lighter, faster, and often just as accurate. The one equation to remember is, HT equals 1 minus ZT times HT minus 1, plus ZT times H tilde T. As a next step for your portfolio, try swapping GRU into your existing LSTM model, maybe the ECG project or a hospital vitals time series, and compare accuracy against training time. That comparison itself makes a great video. That's a wrap on GRU. Huge thanks to Ajay Sir for the teaching, and to my AI friends, Smarty and Claudi, for building this along with me. See you in the next one. Sparky teaches ML.